Good afternoon, everyone. Let's get started. Today, we are going to talk about graphs. These are what we're going to talk about today. First, we're going to talk about the course logistics, and then I'm going to introduce what graph is, and then we're going to have a look at how we can represent graphs in computers, and then we're going to talk about disjoint sets, and if time permits, we're going to discuss how we can travel through graphs. All right, first, course logistics. Homework A was due today and homework 9 will be out today. And there will be one more homework. So in this course, we're going to have 10 homeworks. And regarding YouTube recordings, I did not include the ads, but they are sometimes showing up. Sorry for that. I'm trying to delete the ads, but I'm just in the process of figuring out how to. All right. Regarding course logistics, any questions? Cool, let's move on. First of all, what is a graph? A graph is mathematically consists of two things, a set of vertices and set of edges. So a graph is a mathematical object comprising of a set of vertices, and vertices are also called nodes. And a set of edges, and we represent edges as E, where each edge in E is a two-element subset of vertices from V. So when we are representing edges, we use the representations of vertices. So here are some examples. Let's have a look at the first example, G1, graph 1. Graph 1 consists of V1, and this one has 5 nodes or 5 vertices, and 0, 1, 2, 3, 4. And there are edges. Actually, it has 4 edges. So as you can see here, the difference between G1 and G2 is representing how we represent the edges. In the case of G1, we use parentheses. However, for E2, we use curly braces to represent edges. And as you know, these representations, curly braces, are used for representing sets. And what is one of the most important properties of sets? It is that they are not ordered. So they are unordered in the case of sets. So as you can see here, two-element subsets have 2 vertices, and this means node 0 and node 1 is connected by this edge. And as you can see here, this first edge represents this edge. And in the case of E1, it has parentheses, and this is the starting point, and this one is the end point. So starting from edge 0, it ends up at edge 1. So it has direction. And 0, 1 and 1, 0 are different because 1, 0 represents this edge that starts from 1 and ends up at 0. So these concepts are pretty straightforward, and sometimes we call this kind of graphs as directed graphs. However, when it comes to these types of graphs, we say undirected graphs. So they are different. Anyway, they are pretty simple to understand. So what you just need to do is connecting these 2 nodes or these 2 vertices specified in this E set, edge set. And in the case of curly braces, you do not denote the direction. However, in this case, the first element is the starting point, and the second element is the end point. All right. So that is there are two examples of graphs. One was directed and the other was undirected. And why do we talk about graphs? In fact, graphs are everywhere. When you think about road networks, we use navigation to implement navigation. We need to represent roads as networks, and to represent networks, we need to use graphs because that is the simplest way of representing networks. And we are using internet almost every day, almost every moment. And to represent computer networks, we better use graphs. And when it comes to social networks, we do a lot of social networks. And when we represent the relations between people, like P1, P2, we represent these relations as graphs. And when we do puzzle games like chess or Tetris, Rubik's Cube, we use graphs to solve these types of problems. And there are a huge variety of applications that use graphs. So these are some examples. And there are some terminologies, and I'm going to explain each terminology. A vertex and edge are incident or adjacent. They talk about the same property if the edge contains the vertex. So let's say we have node 1 and node 2 and node 3. And there is one edge between node 1 and node 2. And let's say this edge is E1. And we say vertex 1 and vertex 2 are adjacent or incident. And at the same time, we say E1 and vertex 2 are adjacent or incident. So that is what incident and adjacent mean. And the second term we want to talk about is directed or undirected. We talked about it in the previous slide. If subset pair is ordered using these parentheses or tuple, then this is the starting point and this is the end point. So U and V, like this. So in this case, if edges have directions, then we say the graphs are directed. Otherwise, we say the graphs are undirected if its subset pair is unordered. So we use a set representation to denote the edges. And another thing is, when it comes to directed edge, so U is the starting point and V is the end point. We say vertex U, this one here, is tail. And we say vertex V as the head. Okay? So the starting point is called tail and the end point is called head. And another term is that the edge E is an incoming edge of V. And this is very intuitive because the edge is pointing to the node V. So we say this edge is an incoming edge for node V. And this E is outgoing edge of U. So these terms are quite intuitive. And in an undirected graph, we say every edge is both incoming and outgoing. So we do not distinguish between incoming or outgoing. And the in degree and out degree of a vertex V denotes the number of incoming and outgoing edges connected to V respectively. So as you can see here, let's say this is the vertex V, and there are 3 edges coming towards this node, and there are 2 edges that are coming out of this V. Then we say the incoming degree or in degree is 3 because there are 3 edges pointing to this V. And the out degree is going to be 2 because there are 2 edges going out from this vertex V. So these are some concepts you need to remember. Unless otherwise specified, when we talk about degree, we generally mean out degree. So out degree is more general than in degree. So these are some terminologies we use when we discuss graphs. Okay, that was a brief introduction of graphs. And from now on, we're going to talk about how we represent graphs using computers. And there are 2 typical methods to represent graphs in computer. The first one is called adjacency matrix. I guess some of you are familiar with this concept. This is a matrix with V times V dimensional 2D array for storing edges. And the element at the position I, j or j, I is 1 if Vi and Vj are connected by an edge. So in this case, it is undirected. For directed graphs, we can use different notations. So A, I, and J are going to be 1 if an edge goes from I to J. And then A, J, I is going to be 0 in the case of directed graphs. However, the disadvantage of adjacency matrices is that it uses too much memory. Let's say if we have 1,000 nodes, however, there are only 3 edges, then to represent these 3 edges, we need to make 1,000 times 1,000 matrix. That is waste of memory. And as we have more and more vertices and edges, the complexity for manipulation increases more and more. So these are 2 issues with adjacency matrix. And this is the first method that we use to represent graphs in computer. And the second method we can use is adjacency list. For each vertex, we're going to store the outgoing edges in a list. And this list could be a hash table. So the storing process and retrieving process can be very efficient because we're using hash. And as you can see directly, efficient time complexity than that of adjacency matrix, because we only store the edges, actual edges. So if we have just 3 edges, then we just need to use 3 slots rather than 1,000 times 1,000 slots. I'm going to show you some examples. So let's say we have these 3 graphs, and how can we represent these graphs using adjacency list? For the example 1, this one is undirected graph. And this comment means the vertex 0. So for vertex 0, we have 2 nodes connected. So from vertex 0, we are connected to node 2 and node 1. And in the case of, let's talk about this one. in the case of vertex 1, we have 3 nodes connected. So it is connected to 3, connected to 0. So we are writing down the nodes that are connected to the node 1. So this is how we represent this G1 with this adjacency list. And in the case of directed graphs, we represent, we only store the outgoing edges. So in the case of undirected graphs, for 0 and 2, 0 contains 2 and 2 contains 0. So they are storing each other in the sublist of edges. However, in the case of directed graphs, we only store outgoing graphs. So in the case of vertex 0, it only contains the vertex 2 because it is the only outgoing vertex. And when you see 2, the node 2, it does not contain 0. We do not have 0. However, if it were undirected graphs, then it would have included this one, like this. So we only store the outgoing edges. And here, we are using lists to store there was one question. The ordering inside this list does not matter. So if you store like 0, 2, 3, it is perfectly okay. It doesn't matter. And in this case, you can store 0, 2 instead of 2, 0. All right, so the ordering inside this list does not matter. However, the ordering of these sublists are important because this one represents the edges connected to the node 0. So the ordering of these sublists are important. So in the first 2 cases, we used lists to represent the edges connected. However, this ordering is important. However, the ordering implicitly represent the nodes. And we want to make this one explicit using dictionaries. So we are making the node and the edges connected explicit using dictionaries like this. So node A is connected to node S and B like this. So this node is connected to node S and B. And we write down the name of vertex as key. So in the first 2 cases, the relation between the node and edges were implicit. So the ordering was important. However, if you're using dictionaries, then these keys represent the name of vertices. So the relation between the vertex and edges become explicit. However, sometimes it's not enough to perform all operations for graphs with the adjacency list representation. So I'm going to introduce disjoint sets. In the case of previous representation, adjacency list, it is hard to find the inclusion relation between nodes or edges or vertices. So we're going to use disjoint sets to represent graphs. And once we implement disjoint sets, what I talked about will be clear. But before we move on, are there any questions? Cool, let's move on. And what are disjoint sets? In Korean, disjoint sets are 서로소 집합 or 상호 베타 집합. So they share no common elements between sets. So 서로소 or 상호 베타 집합. And one element of a set represents the set. And we call this element as representative or head or root. So there are many terms indicating this representative element. And using disjoint sets, we can quickly check whether two vertices are connected or not. So in this example, if you want to check whether 3 and 8 are connected or not, we can easily see that 3 and 8 are not connected or are not in the same group. However, for computers, it is quite hard to distinguish whether these two elements are in a common set or not. So that's why we are implementing disjoint sets. And as you can see here, these colored nodes are the representatives or root of this set. So we have 1, 2, 3, and 4 disjoint sets. And this disjoint set contains only one element, and that element becomes its own root or its own representative. And there are some terminologies related to disjoint sets. We say a parent node. So the direct parent node of a vertex is a parent node. For example, the parent node of vertex 3, the parent of this one is 1. And the parent of 2 is 0. And the parent of 1 is 0. And parent of 9 is 9 itself. And the parent of 0 is 0 itself. And we say this parent or representative, a node without a parent node, or we sometimes say a node whose parent is itself is root. So these colored nodes are root, or we sometimes use the term head. And it can be viewed as the parent node of itself. The root node of vertices 3 and 2 is 0. And as for 0, it is its own root node and parent node. Likewise, the root node and parent node of vertex 9 is 9 itself. Okay, that was the definition of disjoint sets. And what are we going to do with disjoint sets? We are going to perform 3 main functionalities. The first one is make set. This one is simply creating a new set containing only X. I told you that there are some sets with only one element. And to deal with those elements, we're going to make set. And we can also implement find set to figure out the set that includes X. And this function returns the representative of the set. So find set actually means find representative or find root of the set that contains X. And union operation unites 2 sets, each containing X and Y. I'm going to show you examples figuratively. So this disjoint set is to solve the connectivity problem. When it comes to graphs, I told you that we could use adjacency matrix. Adjacency matrix or adjacency lists. However, these two representations are not good to solve the problems of connectivity. So we are introducing disjoint sets to solve the problem of connectivity. And in fact, there are two ways of implementing disjoint sets. The first one is quick find, and the second one is quick union. And I'm going to talk about quick find first. So in the beginning, we are going to use this operation, make set. And let's say we have 10 elements, 10 vertices, and we're going to make each one as its own set. So we are calling make set for each element like this. And we end up with 10 disjoint sets. So we performed this make set operation first. And we're going to keep track of the root of each vertices. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we call union 0 and 1, what we are going to do is unite 0 and 1 like this. So 0 and 1 are going to be in a same set. And when we call union, so this one is union operation. We unite the set containing 0 and the set containing 2. So here, the result is going to be uniting 0, 1, 2 in a single set. And when we call union 1 and 3, the set containing 1 and the set containing 3 are going to be united like this. So after we call the 3 method, uniting 0 and 1, 0, 2, 1, and 3, then these 4 elements are going to be in a single set. And when we call 4 and 8, sorry for that, 4 and 8 are going to be in a same set. And 5 and 6 are going to be in a set after we call this operation. And after this operation, the set containing 5 and the set containing 7 are going to be united. So finally, these two sets are united into one set. Okay? And if you want to check whether the given two vertices are connected or not, what we need to do is like this. So let's say in the beginning, the root of each element were themselves. So the root of 0 was 0 and root of 1 was 1. However, after we perform these union operations, we set 0 as the root. Then the vertices 1, 2, 3 are going to be having 0 as its root, as their root. And in this case, we make 4 as its root, and 8 are going to have 4 as its root. And for 5, 6, 7, we're going to make 5 as its root, and 5, 6, 7 are going to have these ones, 5 as root, and 9 has root 9. And when we want to check if vertices are connected, what we do is call this find set operation. So when we call find operation, 0's root is going to be 0 and 3's root is going to be 0, and they are equal. And in this case, we say 0 and 3 are in the same set. They are connected. And the root of 1 is 0, and root of 5 is 5. In this case, these two roots are not the same, so they are not connected. And the root of 7 is 5, and the root of 8 is 4, and their roots are different. And we say these two roots, these two nodes, are not connected. So this is how we implement quick find. And as you can see here, when we unite this and this, we need to update all the roots of the connected vertices. So the union operation is quite slow. Union is slow. However, find operation is quite fast. It takes only 0.1 because we just need to retrieve the root of each one and then check whether they are the same or not. So that is quick find. And once I explain the concept of quick union, you can compare them more clearly. So in the case of quick union, what we do is make union operation quick. So let's say we have vertices and roots, and we're going to keep track of vertices and roots. And when we say we want to unite 0, 1, this one, and then this one, we first update, let's say the root is now 1. And after uniting 0 and 1, we're going to update the root of 0 as 1, like this. And the next step, when we update this operation, we unite 0 and 2. This was originally 2. However, we need to make it 1 in the case of quick find. In the case of quick find, it would be 1. However, for quick union, what we do is we just put 0 here. So for union, it is quite efficient. However, when we want to do find operation, when we want to check whether 2 and 3 are connected, we first need to go to 0 to find the root of 2. And then we go to the node 0, and its root is 1. And we go to the vertex 1 and check vertex 1 has root as its own. Then we say that the root of 2 is 1. So as you can see here, the find operation is quite slow. So these are two ways we can implement disjoint sets, quick union and quick find. So before we implement, let's compare quick find and quick union. In the case of quick find, the find operation took 0.1. However, the union operation could spend 0.n. And in the case of quick union, the find operation was between 0.n and then 0.1. And the union operation was between 0.1 and 0.n. Okay, so can you see the difference? And from now on, we're going to implement disjoint sets. But before we move on, are there any questions? Okay, cool. Let's move on. So from now on, we're going to implement disjoint sets. And the first one we are going to implement is quick find. Okay, let's define class disjoint sets. And I'm going to give you some test cases first. We could create disjoint sets with 10 elements. And after that, we could connect 1 and 2. And 2 and 5. And 5 and 6. 6 and 7. 3 and 8. And 8 and 9. After performing these union operations, you could check whether 1 and 5 are connected or not. And it's going to say, because here 1 and 2 are connected and 2 and 5 are connected, so are 1. So 1 and 5 are connected. And when we want to check whether 5 and 7 are connected or not, it's going to say true. Because through 1, 2, 2, 5, 5, 6, and 6, 7 are connected. So 5 and 7 are connected. And when we want to check whether 4 and 9 are connected or not, it will say false. However, after we union 9 and 4, and then call this method again, it's going to say it's true. So these are some functionalities of disjoint sets. We are dealing with the connectivity problem. And the first thing we need to implement is the constructor. We are going to receive the size or the number of items. And we're going to create a list which keeps track of the root of each node. And we need to implement the find method. And this one returns the root of x, and it takes O1. And implementing this method is very simple. We just need to return the root stored at the position x. That's all we need to do. And we also need to implement the connected method, whether x and y are connected or not. And this is pretty simple. We're going to just return whether the root of x and the root of y are the same. And this one takes the time complexity of O1. And the next method we need to implement is union method. And to implement this method, we need to first check the roots of x and y. And if they do not match, we need to update the roots. Okay? And as I showed you in this figure, the roots of the same roots of the connected vertices should be the same in the case of quick find. Okay, and this is going to be our first PPP exercise. Take some time and try to implement this method. And as usual, please send me PPP message before you start to implement this method. All right, thank you for sharing your answers. Let's solve this problem together. Okay, this one is actually from Hyukjun. We first need to find the root x using the find method like this, and the root y using the find method. We could use just self root x. However, sometimes we might change the functionality of this find operation, and we could remove this attribute. Therefore, it is better to use this find method because it guarantees the functionality of finding the root. And after we did that, if they do not match, if root x is not root y, then what we are going to do is for every root, if self root I equals root y, then we're going to change the root of y as root x. And after this operation, the root of y, the elements whose roots were originally y, are going to become root x. Okay, so it is how we unite two elements. So that was quick find. As you can see here, the find operation is very fast, O1. However, this union operation takes time complexity of On. And let's talk about quick union together. I'm going to copy this code because other functionalities are pretty much the same. I'm going to delete this part. So the init operation is the same, and find operation is going to be somewhat different. And the connected operation is the same. We don't have to do anything for this connected method. So how do we perform find operation? We need to find the actual root of x. So what we are going to do is until x is not the root of itself, we're going to keep following the root x. And after this while operation, we could find x. Okay. And if you compare this find operation with that of the quick find, this is much shorter and faster. However, this one takes smaller than On. However, it could reach On in the worst case. And when it comes to union operation, how are we going to perform union? What we're going to do is we first check the root of x and root of y. And if they're not the same, rather than having this for loop, what we're going to do is, so I'm going to make these 3 lines commented. And what I do is change the root of y as root of x. So the union operation compared to the quick find becomes quite simple. So it takes less than On. So these are the differences between quick union and quick find. And at this point, you might think, so which one should I use to implement disjoint sets? Think about it for like 30 seconds and please send me your opinion, which one is better between quick union and quick find. I'll give it 30 seconds. Think about it. Okay, thank you for sharing your answers. The answer is quick union. Why is it so? We need to think about worst cases. In the case of quick find, we're combining O1 operation with ON operation. And when we are combining these two operations, the worst case is ON. So even though we have O1, the effect of O1 will be minimum when we are calculating the overall complexity. So when we calculated the asymptotical time complexity, O1 plus N or O1000 plus N becomes simply ON. We're going to ignore the smaller part. So the overall time complexity is going to be ON for quick find. And in the case of quick union, the overall time complexity is smaller than ON because we're combining these two operations, ON and ON. So in general, we say quick union is better than quick find. However, there is another way of improving quick union. We want to make this operation better. That is called union by rank. So here, we are just choosing X or Y randomly and set one of them as the other's root. However, this could be very inefficient. And what we are going to do is, I'm going to describe union by rank here. So when we are uniting two groups, rather than just simply concatenating two things, what we are going to do is let's say 1, 2, 3. So in the case of quick union, the height could grow like this. However, in the case of quick find, the maximum height is always 1 because all the elements have the same root in the same group. However, in the case of quick union, the height can grow more than 1 like this. So when we are combining, let's say this group and this group, if we combine this one, the first one, to this one, then the height, maximum height, becomes larger. So 5, 6, and 1, 2, 3, 4, like this. However, if you combine this, if you connect this one to this one, then the maximum height does not change because 5 and 6 goes here. So rather than just blindly connect two groups or unite two groups, we're going to think about the maximum height of each group. And we say the maximum height is rank. So we're going to connect the group that has smaller rank to the one that has larger rank. Okay, so that is the concept of union by rank. Okay, so we need to change some implementation to make these operations more efficient. So rather than just keeping track of the root, we're going to keep track of the rank as well. So at the first initialization step, each vertices will have the rank 1. And the find operation is going to be the same, and the connected operation is going to be the same. However, the thing changes is the union operation. Sorry for that. There is some technical problem here. Okay, resolved. So when we are, we need to just change this union operation. Here, rather than just setting the root of y as root x, we're going to consider the root, the rank. So if the rank of x is larger than the rank of y, then what we are going to do is set the root of y as root x. And else if the rank of root x is smaller than the rank of y, then we're going to set the rank of x as the root of y, like this. Otherwise, this means x and y have the same rank. In this case, what we are going to do is we're going to choose randomly x or y. However, here we're going to choose y and set the root of y as root x, and we need to increase the root of x by 1. So by slightly changing the rank operation, this operation becomes much faster. Okay, so this is one improvement over naive quick union. And another improvement we can do is called path compression. So up to this point, we have made this union operation more efficient. And we're going to make find operation also efficient using path compression. So the other operations are the same. However, the find operation is going to be somewhat different. So I'm going to show you one example first. Let's say we have 5 nodes, 1, 2, 3, 4, 5. And the root of 1 was 2, and the root of 2 was 3, and the root of 3 was 4, and the root of 4 was 5, and the root of 5 was 5. And this is 5 was connected to 4, and 4 is connected to 3, and 3 is connected to 2, and 2 is connected to 1. So this one is similar to linked list rather than a tree. And the time complexity is going to be O(n). However, after the find operation, to find the root of 1, we need to go to 2, because the root of 2, the root of 1 is 2. And we go to 2 and check its root. However, its root is not 2, but 3. So we move on, and we reach 5. And the 5's root is 5 itself. So we say the root of 1 is 5. However, after we do this, why don't we just stay there? Why don't we just update the roots of these elements? So after define operation, we're going to update the root of other elements. We can do this, okay, when we are performing this find operation. And this is called path compression. And this is going to be our next PPP exercise. You can slightly modify this operation and can implement this path compression. In this example, don't think about the rank. Okay, so try to implement this find path compression operation. As usual, please send me a PPP message and take some time and try to implement this method. I'll give you 1 more minute. All right, thank you for sharing your answers. Let's solve this problem together. The thing we need to change is we first need to check whether x is the root of itself. If that is the case, we are going to return x. Otherwise, what we are going to do is update the root of. We're going to call find operation as a recursive function, and we pass the root of x like this. And after this, we're going to return the root of x like this. So this is a recursive implementation. However, you can also implement this one as iteration rather than using recursion. Okay, so that was pretty much about disjoint sets. And the last thing I'd like to talk about is the application of disjoint sets. I'm going to give you this problem and then summarize this lecture. Because we're running out of time, I'll just describe this problem. And then after class, you can solve this problem on your own. And in the next class, at the start of next class, I'm going to solve this problem first. So the problem of all earliest friends is like this. So this logs contains 3 items. The first item is the timestamp. So in 2019, January 1st, the person 0 and person 1 got to know each other. And in the case of this one, in 2019, March 12th, the people 1 and 2 got to know each other. So the earliest friends returns the time when all the members got to know each other. So it wants to return the time, the earliest time when all of them are connected in some way. And in this case, timestamp is 0. So at the time 0, the people 2 and 0 got to know each other. And at time 4, the people 1 and 2 got to know each other. And the earliest time that the 4 members of these people are connected is 3. And if the connection of all the people is not possible, then it's going to return -1. Okay, so this is going to be a PPP exercise on your own. So next class, I'm going to solve this problem in the beginning of next class. All right, this is the end of today's lecture. If you have any questions, you can stay here. Otherwise, you can leave now. Thank you for your participation.